Today we will show how to find the internal force diagrams for a beam carrying a uniform load combined with a concentrated load. For the shown beam, it is required to draw the internal force diagrams. The first step is to calculate the reactions. Then we start by calculating the internal forces at the critical points on the beam. We start at point A by evaluating the internal forces just to the right of point A. As detailed in a previous lecture, we calculate the internal forces at a point by dividing the beam into two parts at that point and using the forces in only one of the two parts to evaluate the internal forces. We are free to use any one of the two parts, but take care that the sign convention for the left part is opposite to that of the right part. For the current point, we will work on the left part. We will display the sign convention of the left part for our reference. Because the beam is not subjected to any horizontal force, the normal force will be 0 for the whole beam. The shear force will be the sum of all the vertical forces in the left part. For this point, we only have one vertical force, YA, which is equal to 7 kN, so the shear force will be positive 7 kN. We draw this value to scale on the shear force diagram. To find the value of the internal bending moment, we take the moment of all the forces located at the left part about the considered point, which is point A. The moment about point A will be 0 because all the forces in the left part pass through point A. Next, we evaluate the internal forces at the next critical point, which will be just to the left of the 3 kN concentrated load located at point C. We follow the same procedure by dividing the beam into two parts at that point, and we will use the left part. We will convert the distributed load in the left part to an equivalent concentrated force, but take care that we will not consider the total length of the distributed load. We will only use the part that is located in the left part to the left of point C with a length of 4 meters. So the equivalent force will be 2 kN per meter multiplied by a length of 4 meters, giving an equivalent force of 8 kN, located 2 meters from point A. The normal force will be 0 as before. The shear force will be the sum of all the vertical forces in the left part, which will be positive YA and the negative 8 kN equivalent force, giving a value of negative 1 kN for the shear. We draw the value in the shear diagram and connect it to the value at point A using a straight line. The value of the moment will be calculated by taking the moment of all the forces in the left part about point C. The left part contains two forces, YA, which is multiplied by an arm of 4 meters rotating in the positive direction, and the 8 kN equivalent force multiplied by an arm of 2 meters rotating in the negative direction. The resulting moment about C will be positive 12 kN. The evaluated value is drawn on the diagram at point C. However, we cannot connect this value to the value at point A using a straight line, because the existence of the uniform load causes the diagram between points A and C to be a parabola. The parabola will be drawn as follows. First, we will connect points 1 and 2 using a straight line. This line is a construction line and does not represent the final diagram. Then we bisect the line at point 3. From point 3, we go up 4 kN in a direction perpendicular to the beam to locate point 4. This value of 4 kN is calculated from the formula WL squared over 8, where W is the value of the load and L is the distance between points A and C, the distance in which the parabola is drawn. From point 4, we go up an identical distance of 4 kN to locate point 5. Next, we draw 3 lines to act as tangents to the parabola. The first tangent connects points 1 and 5. The second tangent connects points 2 and 5. And the third tangent passes through point 4 and is parallel to the line 1, 2. Finally, we draw the parabola as a curve tangent to the three lines and passing through points 1, 2, and 4. Then we evaluate the internal forces at the next critical point, which will be the point just to the right of point C. We will also use the left part and convert the left part of the uniform load to an equivalent concentrated load in the same way as in the previous step. The normal force will be 0 as before. The shear force will be the sum of three forces, YA, which is positive 7 kN, and the negative 8 kN equivalent force, and the negative 3 kN concentrated force, giving a value of negative 4 kN for the shear. We draw the value in the shear diagram and connect it to the value calculated at the previous step using a straight line. The bending moment is calculated by taking the moment of all the forces in the left part about point C. The bending moment will have the same value as the previous step, since the only force added to the left part in this step is the 3 kN concentrated force, which passes through point C and is not included in the moment equation. Next, we move to the point on the left of the roller support at B. Although it is much easier to work on the right part since it involves less forces, we will work on the left part for more practice. So we will display the sign convention for the left part for reference. Next, we will convert the distributed load to an equivalent concentrated force. For this point, the whole length of the uniform load is located in the left part. So the equivalent force will be 12 kN located 3 meters from point A. The normal force will be 0. The shear force will be the sum of three forces, YA, which is positive 7 kN, and the negative 12 kN equivalent force, and the negative 3 kN concentrated force, giving a value of negative 8 kN for the shear. The value of the shear is drawn on the diagram at point B and connected to the value calculated at the previous step with a straight line. The value of the moment will be calculated by taking the moment of all the forces in the left part about point B. The left part contains three forces, YA, which is multiplied by an arm of 6 meters, rotating in the positive direction, the 12 kN equivalent force multiplied by an arm of 3 meters, rotating in the negative direction, and the 3 kN concentrated force multiplied by an arm of 2 meters, rotating in the negative direction. The resulting moment about B will be 0 as expected. This can be easily concluded if we worked on the right part. Next, we connect the moment at point C with that at point B using a parabola in the same way as detailed previously. The value of WL squared over 8 in this case will be calculated as 2 kN per meter multiplied by the square of 2 meters divided by 8, giving a value of 1 kN meter. After connecting all the calculated values, the final diagrams are produced as shown.